what will we find when we go into space? Is there alien life out there, or are we alone in the universe? We will have to boldly go where no one has gone before.
Welcome to the Origins Project at ASU. I'm Lawrence Krauss. The Origins Project was designed to explore the deepest questions that humans have ever asked. We're bringing together the world's greatest minds, the most amazing group of public intellectuals and scientists that's ever been on one stage at one time, in this massive 3,000-seat auditorium where they can interact with each other and the public like never before.
Science!
We have this dilemma that our soon descendants may see things from a hilltop across which we can't see now.
Science is more than a body of knowledge. It's a way of thinking.
When I see a kid open up his or her eyes and say, "Oh my God, this is spectacular," it feels great.
And here to present the Dear Aliens Award, Professor Stephen Hawking.
Science is hard, but it's worth it. It's fascinating, it's enthralling.
Scientists see science as an adventure, and that's why these are adventure stories about discovery and about the thrill of discovery.
And the geek shall inherit the earth.
This is just the beginning. Okay, come on out. So you're there. You're there. Welcome to the first event of the 5th anniversary of the Origins Project. In case you hadn't figured it out, I'm Lawrence Krauss. I'm the director of the Origins Project, and it's hard to believe that it's been 5 years that we've been here and working with all of you, and it is amazing. And I know that every time we have guests, and we have a remarkable group of guests today, they're amazed to think of any place that can get over 2,000 people to come in and listen to science. And so you all deserve a round of applause, and we're very happy to have you. I'm particularly excited with this first event of the year to go back to a subject actually that we hadn't touched until the very first event we did in 2009, which is really the ultimate origin, the origin of the universe itself, or perhaps even a discussion of what happened before the universe began, if such a sentence means anything. We'll see. I have no idea where we're going to go today. But we're asking today the ultimate origins question, which seems appropriate. But before we begin, I just wanted to say we're probably, I hope, in this our discussions, I hope we provoke your curiosity. And in your pamphlet here, you will hopefully have found some question cards. And during the first half of this discussion before the intermission, if you come up with a question, fill it out. And during the intermission, there are boxes in the back or people at the front that will be collecting them. And we'll scurry during the intermission to go through and pick some up. And then we'll have maybe a little bit of more discussion, and then we'll go directly to your questions and try and spend as much time as we can on them. So please write some good questions, okay? Because that'll determine how successful we'll be after that. Now, Charles Dickens said a long time ago, in talking about the French Revolution, it was the best of times, it was the worst of times. I suspect that's a time-invariant statement, because every generation finds itself with new exciting possibilities and new potential crises. And we are living in a time where science has made incredible discoveries and driven us unbelievably forward, so successful, in fact, that we may be approaching the very limits of what we can say about the universe, and maybe getting to the edge of the kind of questions we can actually answer. We don't know. But we have come up with these discoveries with incredible mysteries and puzzles, so perplexing we don't know whether we'll ever answer them. Is that a crisis or not? We'll discuss that. Einstein, in fact, the question ultimately that we want to ask is the one that Einstein asked, although he asked it in a weird way. He said, what really interests me is, did God have any choice in the creation of the universe? And of course, by God, he didn't mean God. It was a misnomer. What he really meant is, are the laws of physics unique? Or if we changed one thing, would the whole universe collapse? Could it be different than it is? And that's really ultimately the question that we're trying to address now. And what we're going to try and address tonight are the opportunities, the challenges, and the limitations of getting there. Now, I think I want to go to my first slide here, if we can. Charles? I like looking at myself, but there we go. Okay. So I often like this quote. I began one of my books with it. But it says, the initial mystery that attends any journey is how did the traveler reach a starting point in the first place? And that's the idea tonight. We've assembled the most remarkable group of scientists from a wide variety of areas of studying the universe to try and bring you to the starting point of the ultimate mysteries that we're going to talk about. We don't have all the answers, but when we get you to the starting point, hopefully we can have a useful discussion. Now, in fact, the choice of this panel is determined in some sense by this image, which is over 3,500 years old. It was first discovered in the tomb of Tutankhamun, and it's now often called by its Greek name, Ouroboros, the snake that eats its own tail. Sometimes it's a dragon. And it's, of course, a wonderful analogy. In fact, as far as I know, my colleague, I think Shelley Glashow was the first person that I knew who used this. But because the universe is expanding, it creates a kind of Ouroboros. Because the fact that it's bigger now than it was yesterday and going backwards and backwards and backwards means that if we look at the largest structures in the universe today, if we go back in time, they were contained all in a region smaller than the size of an atom. And that means if we think about the mysteries of the largest scales we can see, if we go all the way back, they were probably determined by the physics of the very smallest scales. And that's why we've assembled here a group of the leading scientists around the world looking at the two different scales to try and understand together what the fundamental physics of the universe is. And the discoveries we've made are incredible. We'll see that we've been using the Gothic cathedrals of the 21st century. The Gothic cathedrals were created over a century by thousands of artisans, speaking dozens of languages. We now are using the most complicated devices that humans have ever assembled, just as they were in the 11th and 12th century. Our machines are much more complicated. The Large Hadron Collider, which we'll talk about in a minute, located underground in Geneva. If you look at that map, you can see the airport in Geneva. If you look out, you'll see farmland. You'd never know underneath it is the most complicated machine humans have ever constructed. Created by thousands of physicists over several decades, speaking dozens of languages, lots of cultures and religions, all speaking the common language of science. The fact that science can bring these together, and people from a diverse set of backgrounds can build devices that have to work together at the level of microns, build these incredible mammoth detectors, which we'll hear Maria talk about. This is called the compact muon solenoid. It's a device that actually contains an equivalent amount of metal as the Eiffel Tower. I have a better picture of it. It's much better because I'm in it. But these devices make you feel like you're in a Jonathan Swift novel. You're just so small. And the complexity of these machines, this machine to try and answer a fundamental question about nature is amazing. I think I just put this down, that every second at the Large Hadron Collider, enough data is generated to fill more than 1,000 1-terabyte hard drives, more than the information in all the world's libraries. That's caused us to try and develop whole new ways of sifting information, which inevitably will feed down into the way modern technology works. And of course, as you all know from the news, the ultimate goal, the initial goal of the Large Hadron Collider was to discover something called the Higgs particle. And Maria will talk about that, I'm sure. The Higgs particle is amazing because it tells us something strange about the universe. Those of you who grew up in Phoenix may not recognize these are icicles. And if you look at them in a window, they're a beautiful pattern, and you can see them pointing in all directions. But if you lived on the backbone of one of those icicles, if you were a small being there, then the world would seem very strange. One direction would look very different than the other directions. It would just be an accident of your existence. What we've learned with the Higgs particle, now that it's discovered, is that's why we're here. An accident of our existence. The Higgs field froze in the early universe in a certain way, and some particles, as they move through a background field, interact more strongly and act more massive. Other ones interact less strongly and act less massive. It's an accident of our existence. If the Higgs field wasn't there, the particles wouldn't behave the way they do, and we wouldn't be here. And that's remarkable that we've discovered that, but at the same time it brings up the important question, why did it freeze the way it did? Why did it establish that force, the forces and masses of the particles at the scale they are? The Higgs particle was the capstone of one of the greatest intellectual quests that humans have ever taken, producing the standard model of particle physics. And we're very pleased on stage to have two people here tonight who happen to have been a central part of the standard model, developing the standard model, and won the Nobel Prize for that. As I said, in fact, when they won the Nobel Prize, I was interviewed, I said, how often do you get to discover the nature of one of the four forces in the universe? The answer is 4 times, actually. But we're very excited by that. But at the same time as this beautiful standard model exists, we don't know why it has the properties it does. We don't know why the Higgs particle has the properties it does. And the question is, will we ever know? That's on the very small scale. On the largest scales, well, actually, I actually put this picture up because I happen to like this period of art. And Impressionist art is beautiful if you stand far away. But if you look up very close, it really stinks. And that's the way the standard model sort of is. It's a beautiful model, but when you start to ask these detailed questions, there are tons of it doesn't seem as pretty. And we want to know why it is the way it is. One of the possibilities is that maybe the standard model is an accident of our existence. I put this figure up here to upset my friend David Krauss because it suggests that maybe there are many universes. String theory, which he was involved in the development of, some people would argue there are many, many different universes. And they form in different ways as extra dimensions compactify. Maybe the laws of physics are different in each universe, and maybe our weird standard model just happens to be an accident. In which case, the laws of physics becomes an environmental science, God forbid, because it means there's no fundamental theory, perhaps. And the question is, how can we discover that? Now, the largest scales. I have the Hubble Space Telescope, and Wendy Friedman is one of the leaders of the programs in the Hubble Space Telescope. It's produced these beautiful images that have inspired many of you when you go on the web. This is the Hubble Deep Field. Every dot in this image is a galaxy. We now know there are over 100 billion galaxies in the universe. If you take your hand up on a dark night and hold a dime-sized hole in the sky, if you had one of the largest telescopes in the world, as the type that Wendy is working on, you could see 100,000 galaxies. And moreover, these telescopes have allowed us to look back in time and far into the distant past and far, far away, long, long ago. Here is a cluster of galaxies. Clusters are the biggest bound objects in the universe. This particular cluster of galaxies is 5 billion light years away. But you don't have to be a rocket scientist to see these weird blue things. Those blue things are multiple images of a single distant galaxy located 5 billion light years behind that cluster. That image is magnified and distorted by space itself. Einstein told us in 1936 that the light bends in a curved space, and space gets curved if matter is there. So the fact that this cluster exists curves space, magnifying that distant galaxy, and allowing us to actually weigh this cluster and weigh the universe. And we find out most of the mass in that system is invisible. It doesn't shine, and physicists, because we have such great linguistic characteristics, call that dark matter. But what's really neat is we think it's a new type of elementary particle, as I'm sure Frank will probably talk about. And what's exciting about that is that we can not just look out there for it, but we might detect it directly in laboratories here. And in fact, we're having a meeting here at ASU where people have talked about the incredibly bold effort to try and detect the dark matter. And maybe we'll get into that. But we can look not just out at galaxies, but we can look back almost to the Big Bang. This image is of the cosmic microwave background radiation, the afterglow of the Big Bang, that comes to us from a time when the universe was only 100,000 years old. And those are hot spots and cold spots in the microwave background. And they were created, we think, at the beginning of time. perhaps by quantum mechanics itself, when the universe began. And what's really exciting is at the same time as we have these new observations, we have great new theoretical tools with massive computers. This is a simulation, this movie is a simulation of not our universe, but a universe as it might be, putting in hypothetical dark matter particles, 10 billion of them, and using the laws of physics to calculate the gravitational interactions of each to produce a universe that you can fly through. And then we can try and compare the characteristics of that universe with the universe we live in, and that's one of the reasons we think the dark matter is made of some new type of elementary particle. But we don't know what it is. And the question is, will we ever know? What happens if the current detectors don't detect it? What do we do next? Finally, we've been able to look at these amazing objects, and Brian was able to look at these objects. This star here, this is another galaxy not too far away, about 60 million light years away. And you see this bright object here on the bottom, which is as bright as the center of the galaxy. That object is so bright because it's a star that's just exploded. And Brian pioneered an effort to be able to use these objects to determine how fast the universe is expanding. In fact, as I'll describe, he led an effort to try and figure out how the universe is slowing down due to gravity. And then he and two groups published this material, which may not look like much, but it won him a Nobel Prize. Because he discovered, to his amazement and our amazement, that the universe isn't slowing down, it's speeding up. It's speeding up with a kind of cosmic anti-gravity. How can that be? Well, it turns out that empty space can weigh something. That if you actually use quantum mechanics and relativity, empty space is a boiling, bubbling brew of elementary particles, and maybe empty space can have energy. You can get rid of all the particles and the radiation, and it still weighs something. But the problem is when we try and figure out how much it should weigh, the answer we get is 120 orders of magnitude bigger than the number that actually happened. It's the worst prediction in all of physics. And the question is, will we ever understand that? Why is the energy of empty space both non-zero and so small? It's perplexing us that we say maybe, well, some people have said maybe there are many universes. And maybe only those universes that have an energy that's that small allows people to come to Gamage Auditorium. And so maybe even this fundamental parameter of the universe is an accident of nature. We don't know. Ultimately, the other aspect of the accelerating universe is that galaxies as we look at now are moving away from us faster and faster and faster. And the longer we wait, the less we'll see. Ultimately, all of the galaxies we now see in the universe in 2 trillion years from now, not for us, but will have disappeared. And the universe will become cold, dark, and empty. That's your future. But it tells us that, well, in the far future, observers won't be able to see what we can see now. But maybe we're stuck in that. Maybe we should have a kind of cosmic humility. Maybe there are things we could have seen 5 billion years ago that we can't see now. Maybe we are limited in the fundamental questions we can ask by our circumstances. We don't know. And those are the kind of questions we're going to address today with this remarkable panel, which I'll introduce now. Okay, the very first person I want to introduce is Maria Sparopoulou, who's a professor of physics at Caltech. Maria is a particle experimentalist extraordinaire. She was at CERN as a senior scientific researcher for many years before moving to Caltech, and she's one of the leaders of the experiments at the Large Hadron Collider, which takes an incredible effort. And it's actually particularly appropriate that Maria is studying one of the 4 forces of nature, because if you know her, you know that she is indeed a force of nature. Maria.
Thanks, everybody. Thanks, Lawrence. Before I start, Mark, are you here? Can you stand up? Good. I want to introduce to everyone Mark Siski I know him from 10 years ago. He was a high school student and my first high-energy physics student at the Tevatron, and he's teaching now at ASU. Thanks for coming. I will talk about the Higgs. I will not be as dramatic as Lawrence, but I want to impress on you the gravity of the situation. And to do that, I will start with a little story. When I was the age that, when I was 19, and that was 4 years ago, I was traveling to Geneva to go to my first technical summer school in Geneva as a technical student. And I caught this flight, and somebody was sitting next to me asking me, what are you going to do in Geneva? And I said, I'm going at CERN, and I have all these things to do, and we're going to discover all these things. And the person was very serious and very elegantly dressed, and he said to me, oh, those physicists, they can't even find out how mass comes about. So I looked at him and I said, I guess we're going to have to wait this one out. Yeah. And we did. And 25 years later, we have it. We have discovered it. And I'm saying this because it takes a lot. It takes a lot of time, a lot of energy, a lot of people, a lot of dedication. It's a struggle. It doesn't come from one day to the next. So with this, let me tell you that I started at the Tevatron as a graduate student. It was a 5,000 tons detector there. It was called the Collider detector at Fermilab outside Chicago. And my 25 years brought me to the 15,000 tons detector that Lawrence showed you called the compact muon solenoid. And this is some of the pictures along the way, starting from back then at the Tevatron. Now, you all heard about the discovery of the Higgs particle. In fact, on this slide, you can see after the discovery announcement at CERN on July 4th, we got a letter from Peter Higgs thanking us for his Nobel Prize because he was sure he's going to get it. Mm-hmm. And that was just a month afterwards. On the right side, you see a dedicated volume of all the results from both experiments, from ATLAS and CMS. And in one line, when I say the H boson, the Higgs boson, indeed, that is the new fundamental force that Lawrence was talking about. It is the only, the first new particle beyond the photon and the electron that has spin zero and is an elementary particle. And with the Higgs, we think we can connect all of the phenomena that Lawrence talked about at the big scale and the small scale. Incidentally, in this dragon thing he showed you, we are the tail. I wish we would have been the mouth, but it doesn't work like that. This is an example of one of the golden channels of how, as we accumulated the data, we started seeing an excess over the background. The background prediction, in other words, the knowledge we have prior of what we expect to see, is the blue histogram. The data is the dots. And if there was a Higgs at 125 GeV or 126 GeV, it should look, which is the mass on the horizontal axis, it should look like this tower that you see with the red. When we saw that, and you see how the data track that, we knew that we have a discovery, and this was a moment where we really had the eureka moment. Now, I want to show you how the events look like in the detector. These are real events. We have the collisions of the 100 billion protons that come in bunches, and we produce, what you see here is we produce, let's say, 4 tracks in both cases up and down at the collision. And these 4 tracks, if you take their invariant mass, it gives you one of the candidate events under the histogram with the red. It's a Higgs event. Who discovered the Higgs boson then, you might ask? It's about 10,000 people, 20 years. This is only one of the collaborations, and it's not the full one. And it's an effort that it works across cultures, it works across nations, and it works across many decades. So this is the compact muon solenoid experimental collaboration with some of the members there. We are about 3,000 with 165 institutions from all over the world, with 600 graduate students and 900 postdocs. Just to give you a sense of how the experiment was built underground. There are two of them of the general purpose, the Atlas and the compact muon solenoid called CMS. And this is the Atlas one, and what we're going to see is underground how the lapse of 4 years, how one part of the detector was actually built. This is very fast, but this covers about 3 years in building. These detectors are meant to capture the energy of the particles and reconstruct the momentum. And when we have the actual particles, we can actually do the analysis with a lot of data. The mention was 1 terabyte per second. Indeed, in 1 terabyte per second, we do event building with 1 terabyte per second from the detector. It's about 100 billion channels, 100 million channels that we have. This is before we started the collisions, and you see here the fit of the LHC is the dipole magnets. Why am I saying this is a fit? It's because we've got protons against protons in one magnetic field, and we've got same sign charge particles going against each other in the same magnetic field. This was a magnet development that was from Brookhaven in the late 70s here in the United States, and LHC adopted this after the SSC was gone. I wanted to say that as you walked through the tunnel here, you saw two tunnels because you saw the cryo pipe, which has about 100 tons, maybe 90 tons of liquid helium in order to chill the superconducting magnets that we have. We've got about 11,000 amps in these superconducting magnets. The magnets are important because they keep the particles in this 27-kilometer tunnel. Now, I want to say that big data and big models and data in motion, this is our trademark. We started this in high-energy physics, in particle collisions. At the Department of Defense, I got this slide where they showed the internet before the LHC, and it is signified by this little dot. And the traffic of the internet and how it evolved in terms of networks, in terms of intelligent networks, data transfers, and exactly how our computing model works has surpassed, in order to be able to sustain the LHC data, has surpassed any technology. In fact, we're talking with Google because we are handling more data per day than Google in months. And I want to close with this pie chart, which is a chart of the questions. We think we have answered a lot with the Higgs boson, but there is a remaining set of questions that are showing the mystery of our universe. Our universe is not a place that we can describe. When I started, I thought I was getting into the point where I would be able to say how the universe started, how the universe evolved, and where it's going. And the more and more experiments I do, and the more I learn that I need to know more before I can actually even comprehend the question that I started with. I will leave it with that. Thank you.
Frank? Okay, well done. Frank, have a seat. Wait till I introduce you. Yeah, there we go. Our next speaker is Frank Wilczek. A friend and collaborator of mine for over 30 years. I remember the very first time I met Frank, I was very disappointed. Because I was a postdoc at Harvard at the time, and Frank was famous. And we met in Aspen, and then I discovered Frank was 3 years older than me. That's why I was disappointed. Frank won the Nobel Prize for work he did when he was 21 years old as a graduate student at Princeton University. Now, you might say he was just lucky to have a really smart advisor, and he was, over there. But that's not it. If that's all Frank had done, he'd still be a famous physicist. But what's happened in the interim is that Frank has become clearly recognized as one of the most creative physicists, particle physicists around, having worked in so many different areas and made fundamental contributions in all of them. And as a collaborator of mine, I'm constantly amazed. Frank knows, when it comes to science, virtually everything, or that's what he tells me on a regular basis. Now, Frank has won many prizes, but I have to say this week I know he's most excited. Can we come to the first slide? Because he sent to all of his friends and family, this is the most prized possession he has. Charles, can we get his first slide up there, for which I've added a little bit? If you know Frank, Frank has a little thing on his wrist, and he's very excited that he's now climbed 500 sets of stairs this year, and he got a helicopter badge. So I think we should all give him a round of applause. Frank Wilczek.
Thank you, yes. Well, to begin, I'd like to show a brief video that will define a technical term that will be of use be of later use in my talk.
Did you know that the Chinese use the same word for crisis as they do for opportunity?
Yes, crisis-tunity.
Remember that word. It might be better to refer to the cosmological dark matter problem as the excess acceleration problem. But in any case, it's a very real phenomenon. If you scan the sky with a powerful telescope, you'll discover that in certain directions, the image is distorted. It's as if you're looking through a very big droplet of water. The explanation is that gravity bends light. And this is a nice picture of the concept that if gravity is bending light, the images you see get distorted. The problem is, or the remarkable discovery is, that the light is getting bent even where there's little or no visible matter. So there's plenty of gravity even when there's very little matter. As a result of this, and many other concordant observations, there's now a general consensus that the part of the universe that we've been dealing with for millennia, the kind of matter we're made out of and learn about in physics and chemistry, is actually, by mass, only a small component of the universe. About 4.6%. The rest is other stuff. No presently known form of matter fits the bill for this other stuff. Neither what we call technically baryonic matter, or non-technically atoms, nor photons, nor neutrinos, nor anything else that we've encountered previously. This situation might seem to warrant humility. But I see it as a crisis-tunity. Because this problem, as I'll demonstrate to you, connects to other ambitious, beautiful ideas that we've been having in surprising and tantalizing ways. So, first let me discuss the question of unification of the forces of nature and supersymmetry in particular. Our standard model gives us a detailed and battle-tested picture of what ordinary matter is, based on two kinds of ingredients, two kinds of fundamental building blocks that technically are called fermions and bosons. Non-technically, you can think of them as substance particles and force carriers. So electrons and quarks are examples of the substance particles, and photons and gluons are examples of the force-carrying particles responsible for the electromagnetic and the strong forces. We can construct beautiful theories that unify these forces and unify these substances so that they can be seen as one substance and one force. One substance that you can view from different angles and can transform in different ways to appear like all the substances we encounter, and one force, one basic force from which all the others are derived. Unfortunately, when we use the techniques for which David Krauss won the Nobel Prize to test this hypothesis that there's one underlying force to which all the others, from which all the others derive, it doesn't quite work. In this plot, as you go to the right, you're going towards shorter and shorter distances where the unification of forces will be revealed if it occurs, and you can see that they almost but not quite meet. So, to quote Homer Simpson, "Dough!" But faced with this chrysotunity, some of us considered the possibility of an even more ambitious unification. The possibility that having two different kinds of things, substances on the one hand and forces on the other, might be one too many. Maybe there's only one kind of thing. That idea is called supersymmetry and would complete the unification. And if we assume supersymmetry, we can revisit that calculation of the unification of forces. And now it works. And there's more. These three forces that dominate the world of particle physics, the strong electromagnetic and weak interactions, and dominate everyday life and chemistry, are not a complete description of nature. There's a fourth major force which dominates astrophysics and large-scale phenomena, the gravitational force. What about it? Well, if you calculate it, you find that it also fits roughly, even though the theory wasn't built to do that. It just happens in an unforced, natural way. So this is extremely tantalizing. Supersymmetry, when it's implemented in equations, requires the existence of new particles. These new particles have not been seen yet. That's all right because they're predicted to be heavy, and almost all of them are unstable too. And those that aren't unstable are shy, in the specific sense that they interact very feebly with ordinary matter. However, heaviness and shyness, with all those very elaborate detectors, is no longer going to be an excuse as the LHC gains its full power. So these particles really have to materialize at the LHC. If one of them is stable, it could contribute some or all of the dark matter, and that makes the connection to this other chrysotunity. Now I'd like to discuss a third chrysotunity. Okay. It is a strange and mysterious feature of microphysics, and has been for a couple of centuries, that it looks almost the same when run backwards in time. If you take an ordinary movie, say Groundhog Day, and run it backwards in time, it would look very, very strange. But if you took a movie of events in the micro world, subatomic interactions, atoms doing their thing, and ran it backwards, it would be almost impossible to tell the difference. The laws work forwards and backwards in time. Finally, that mystery was successfully addressed in the Standard Model when it was properly understood that this funny feature of the microphysical laws is an accidental feature and an only approximate feature, although a very good approximation, a result of other profound principles. And this is work for which Kobayashi and Masukawa won the Nobel Prize. But actually, they shouldn't have. Well, they should have, but their explanation is not complete. It leaves a big loophole. So there are other Nobel Prizes lurking here, maybe. There's one possible source of asymmetry between the directions of time that their theory doesn't address. We can close the loophole by embedding the Standard Model in a bigger, more symmetric theory. When we do this, we find we get a remarkable new kind of particle, the axion. And when you work out how axions behave in the Big Bang, you find that they're likely to supply most of the dark matter of the universe if they exist at all. Now, at our workshop, Professor Sushkov described experiments that should be capable of finding these axions if they exist at all. These experiments, which I think very plausibly will have a positive result, would be epical if they do. They would prove all at one stroke that axions solve this puzzle completely now of why there's time reversal in the micro world. They would tell us what the dark matter is, its axions. They would also, and I'll have to leave the explanation of this for the question period, they would also provide compelling evidence for the fact that the universe underwent a period of rapid expansion, inflation, and that the part of the universe we see and have regarded for a long time as the whole universe is only a small part of a much larger whole, a multiverse. Thank you.
Thanks, Frank. Okay.
And
High five.
Thank you. That will give us a few things to chew on. Next, I'd like to introduce Wendy Friedman, who's the director of the Carnegie Observatories. Wendy is perhaps the most distinguished astronomer in the world. She's actually now in charge, as you'll probably get to see from some slides, of an amazing telescope that's also now being built, the Giant Magellan Telescope, which is unbelievable, and I'm sure we have some pictures of it. But Wendy also, the Hubble Space Telescope was called the Hubble Space Telescope for a reason. Well, two reasons. In honor of Mr. Hubble. But Mr. Hubble became famous for showing us that the universe is expanding, and we want to know how fast. And when that telescope was built, a collaboration was set up to determine how fast the universe was expanding using that telescope. And the person who helped lead that collaboration and was chosen because of her incredible expertise was Wendy Friedman. She has been involved in basically almost all the major developments in astronomy in the last few decades. And what is also amazing about Wendy is that for me, she demonstrates a remarkable fact that you can be incredibly accomplished, incredibly well-known, incredibly prestigious, and incredibly nice. Wendy.
Thank you, Lawrence. I'm going to actually step back and consider a little bit of history before we go on. I feel like I should insult Lawrence, but I'll resist the temptation. Thank you for the introduction. So in the 20th century, a number of discoveries occurred. The expansion of the universe, the discovery that there was dark matter that had an influence on how the light matter, the luminous matter that we see in galaxies is moving, and that we see in galaxies as motions of stars, how they're affected by the presence of dark matter, and also the acceleration of the universe, for which Brian Schmidt was awarded the Nobel Prize. Now, the expansion of the universe, and that's interesting, that's... Okay, I was going to ask you that. I want to make sure you're awake because you've been sitting here for a long time in the dark. Expansion of the universe was discovered empirically, true or false? Very good. And, of course, in the early part of the latter century, telescopes were developed and built at Mount Wilson in Pasadena, California. That's where Edwin Hubble at the Carnegie Observatories made his discoveries with the 100-inch telescope at Mount Wilson, showing that the universe is undergoing an overall expansion. It's filled with galaxies, 100 billion such galaxies. He made those discoveries by using a particular kind of star. We call it a Cepheid variable. It's been known since the 1700s. And he was able to use these stars as very accurate signposts of the distance scale of the universe. Using the distances and also measured velocities, he was able to show that the universe is appearing to expand with time. If you run that as a movie in reverse, that would lead to a time in the universe where matter was much more closely an early time in the universe when matter was closer, it was hotter, and of course fitting in with Einstein's general theory of relativity that had been developed in 1915 or so, led to this picture of an expanding and a Big Bang universe, began with a hot explosion. Now, existence of dark matter was not predicted theoretically. True or false? Let's see if you are out there. Any guesses? True or false? Was not predicted theoretically. Well, the existence... Okay, so if we go back to the 1930s, Fritz Wicke at Caltech, shown there on the left, a rather colorful character. He, in fact, referred to his colleagues at Caltech, I don't know why, as spherical bastards. And why? Because in any direction you looked at them, they were still bastards. And Fritz Wicke made the observation when he looked at galaxies that were in the Coma cluster, a nearby cluster, a very well-known cluster of galaxies. The galaxies were moving faster than they should have been moving if they were responding to the matter that was in the cluster. So the luminous galaxies would have flown off a long time ago if they weren't being held there by something that we couldn't see. And those observations were in fact ignored for a very long time, decades in fact, because it seemed too extraordinary that there was all this matter we couldn't see. And in the 1970s, Vera Rubin, another astronomer at the Carnegie Institution in Washington, D.C., our sister department, made the discovery that as she looked at the motions of stars within galaxies, these are stars now within galaxies, they were moving faster than they should have been if you predicted their speeds based on the matter that we could infer from what we saw. And this gave rise eventually, with a lot more different kinds of observations, which I won't go into, to the idea that there was much more matter than we could see. The expansion of the universe was discovered empirically, and that should be acceleration of the universe. And I think we're repeating slides here. True or false? Okay, so there's a common theme here. And we were talking the other day at lunch at the workshop, and I think David Gross made the comment that some of his Nobel colleagues thought that astronomy or astrophysics didn't have much to contribute to fundamental physics. But it is a fact that the expansion of the universe, although the possibility of expansion was in Einstein's equations, he didn't have the confidence at that point to say the universe must be expanding or contracting. In fact, it wasn't stable. But he put that a term called the cosmological constant into the theory of general relativity to force the universe to be static. Could have predicted it, but he did not. So astronomical telescopes and astrophysics in general has really contributed in the last century to very fundamental changes in physics. And so here, again, Brian's and others' work determining that the universe is not only expanding, it is accelerating, indicating the existence of a tension, essentially, something that is causing the universe to speed up in its acceleration, some kind of repulsive energy. Now, the Hubble Space Telescope and telescopes in general, as I'm arguing, have been instrumental in our understanding of the universe. This is something, as Lawrence mentioned, I've had the good fortune to be involved in. We used the Hubble to improve on the measurements of the expansion rate of the universe and charting the distance scale of the universe. And by getting above the Earth's atmosphere, we were able to make much more accurate measurements of the distance scale of the universe. And I have the dubious distinction of making the universe younger than it was, according to at least a colleague of mine who had an office in the same building, who believed the universe was older. He was also older, it was pointed out to me. So we have two outstanding mysteries, dark matter and dark energy, as we've heard many times already this evening. And we don't yet know what 95% of the universe is made out of. All the stuff that we know about the carbon, oxygen, nitrogen, the things that give rise to life are but 4% or so of the overall mass plus energy content of the universe. Now, galaxies are our signposts of the distant universe. Although most of the matter we cannot see, matter and energy, we use galaxies, the luminous matter, to actually see what's out there as an indication of the overall mass. These are but small portions of what's called the Hubble deep field or ultra deep field. And literally, if you take your small finger and look at the Hubble, look at the sky in an area which is blank, for example, on the Palomar Sky Survey, there were no galaxies in the region that was originally chosen, and then you integrate for several weeks with the Hubble Space Telescope. There are literally thousands of galaxies in these images, and the bigger galaxies tend to be the ones that are nearby. The faint little smudges are galaxies at very great distances, and telescopes, in fact, are our time machines. Because of the finite speed of light, 186,000 miles per second. As we look back farther away in the universe, we're seeing galaxies as they were when the light left them. So literally, galaxies are time machines. And we saw some beautiful illustrations earlier of these arcs. You can see these blue arcs. Regions, again, clusters of galaxies with a lot more mass. And as distant galaxy, the light from distant galaxies is coming through the mass, through the cluster, their light is bent, as Einstein's theory predicted. Another indication of dark matter. What's coming up in the next less than a decade? The James Webb Space Telescope is going to be a successor to the Hubble Space Telescope. It's a 6.5-meter telescope. And due to be launched in 2018, it is sensitive to infrared radiation, and it will be about 1 million miles from us, and not unlike Hubble, unable to be serviced in the way that the Hubble Space Telescope was. And just for reference, that's the distance to the moon. It's got about 2.5 times the resolution of Hubble. And the Giant Magellan Telescope that Lawrence mentioned, this is a telescope for which a leader of this project is a 25-meter telescope. It will be located in the Andes Mountains in Chile. It will have a spatial resolution that's 10 times that of Hubble Space Telescope, more than 100 times its sensitivity. So Lawrence asked us, when he asked us to be on this panel, to think about how we would continue to probe fundamental physics and the origin of the universe, and I would submit that astronomical telescopes will continue to be a vital probe. Many new facilities on the horizon that are coming up, and I think as we continue to learn about the nature of the dark sector of the universe, 95% of the universe, when we think of the complexity in chemistry and biology and this tiny 4% that we know a lot about, it's hard to imagine that there aren't going to be a lot of details in the dark sector that we can't even imagine at this point. And I will just leave you with a simulation again, this millennium simulation that Lawrence showed. On the right is an indication of where the dark matter particles are. These are, of course, numerical simulations done in a computer, 10 billion particles or so. The galaxies, the luminous material is on the left, and it's only about a sixth or so of the overall matter. Again, the only way we will learn on the larger scales what the behavior of both the growth of structure in the universe and the behavior of dark matter on large scales is to look at these luminous signposts. So I will stop there. I think I'm more than out of time.
Got fans. Okay, Brian Schmidt. Brian is still pretty young, actually, but when he was 27 years old, and still a postdoc, he led a collaboration of people, many of whom were more than twice his age, which says something, to try and figure out how fast the universe was slowing down. And the fact that he could put together that collaboration and make it work at such a young age, and the fact that they let him, tells you that people already had great respect for him. As you now know, that collaboration discovered something remarkable. What they were looking for was wrong. The universe wasn't slowing down, it was speeding up. That is, in the minds of many physicists, and perhaps the most astounding discovery of the last 100 years. Totally unexpected. And for that, he and several of his colleagues deservedly won the Nobel Prize. Brian is located in Australia, Mount Stromlo Observatory, where I'm privileged to spend a few months a year, every year, as a colleague of Brian's. And I thoroughly enjoy that. Many people go to visit Brian in Australia. When you go there and you give a talk, it's not because Brian is there. It's because Brian's wine is there. Besides being a remarkable scientist, Brian is a remarkable winemaker and makes one of the best wines in Australia. And if you give a talk at Mount Stromlo, you are presented with a bottle of Brian's wine. We don't have a bottle of wine for you here, but begin.
Thank you. Yeah, unfortunately, I have the distinction within astronomy of being that astronomer who's a winemaker, and within the winemaking community, I'm that winemaker who's an astronomer, which tells you what everyone thinks about what I do in my field. So I'm going to get deeply philosophical here to begin with. And I want to go back to the beginnings of modern astronomy, to the time of Copernicus. Now, Copernicus had this great idea. And that idea was he could look at, for example, the planets, Venus here, and he could explain its motion and the motion of the other planets in a way that was different than had been accepted by people before him, which is that he had the sun at the center rather than the earth, and the planets went around it. And it was a great idea. The only problem is when he went through and predicted where the planets would move, he couldn't predict their locations as well as the Greek system of having circles within circles within circles. Now we know that that Greek idea, which had evolved over 1,000 years, was very complicated, but was built up on an axiom, which is that the Earth must be the center of everything. So Copernicus's idea did not really gain much traction until it was experimentally verified. And that came from Galileo. And through improving a telescope so that he could look at Venus, he could see that as Venus went around in its path, it had phases like our moon, such that when it was behind the sun, it looked like a full Venus, and when it came around, it was a crescent. And so by an observation, he was able to take Copernicus's idea and turn it into what we would describe as reality. And I argue that everything that we take in life to be reality is based on a set of ideas that predict things that come true in life. And we hold that to be very true because when we think we understand something and suddenly it doesn't work, we question the reality in front of us. Now, this isn't true just in this case. It's true from a variety of things. For example, Einstein had an idea. He had an idea that acceleration due to gravity and acceleration to just moving more quickly were equivalent. It was a small idea, but it took him 8 years mathematically to figure out the consequences. And the consequences was that space would be curved. An interesting idea, but one that became real when you were able to observe an eclipse and see that during that time the stars' positions were bent by the curvature of space, and when the sun was gone and you looked at that place, you could see that the stars had moved. Once again, an idea has become real because of an observation. And this has gone throughout astronomy, and so astronomy has really been a field where we have had technology meeting ideas. Sometimes technology leads. So, for example, Herschel in 1781 was out looking at a field, and he saw a blob, now known as Uranus, moving across the sky. He could tell it was a planet because it didn't look like a star, and it moved in the track of a planet. So he was able, through technology, to make a new discovery, the first planet discovered since, all of humanity. But immediately there was a problem, because you could use Newton's laws, and you could see where Uranus should travel, but it did not follow the path that Newton suggested. So was gravity wrong? Did we need to have a new force, a new way of describing gravity? Well, possibly. Or it turned out, as a French astronomer realized, or a mathematician, that you could posit that there was another object there that was pulling on Uranus and making it deviate by gravity and Newton's laws. An idea which, through a rare piece of German and French cooperation in the 19th century, led to the discovery of Neptune. Now, of course, if Neptune wasn't there, we would have probably had to think about modifying gravity. But instead, the simpler idea of there just being another planet there undiscovered was what made that idea a reality. In the 1930s, we had technology and the ability to make observations with telescopes that could see large parts of the sky at a time. This gave us the notion of discovering Pluto, the planet of the 1930s, seen here moving very slowly across the sky. It's a very faint star. Through the understanding of how our solar system formed, we were told, at least when I was taught in school, that there should be objects like Pluto beyond Pluto. They should exist, but they had not been seen until we got new digital technology, which was much more sensitive. And in these images, you see the new object named Eris that took Pluto and demoted it from being a planet to a dwarf planet. So once again, we have an idea, you test it, and in the process of technology, you go through and test your ideas. We can do this, as we have seen very elegantly here on Earth, with something like the Large Hadron Collider, where you have an idea from 1964, that's 3 years before I was born, and through long, hard work, it has been tested, and we know that that idea is reality. And so you were able to discover the Higgs boson through this process of technology meeting a theoretical construct. Now, as Lawrence said, we went out in 1998 and measured how the universe was expanding back in time by looking at objects billions of light years in distance. And we were expecting, as indicated, to measure how the universe was slowing down, because I wanted to find out if the universe was going to expand forever or eventually stop expanding, go into reverse, and end in what we like to call the Gnab-Gib, which is the Big Bang backwards. Now, sometimes you get lucky in life, and I certainly did with the team of 20 people that worked with me, that you get something that is just a surprise. You measure something And in our case, unlike the CMS team, we did not have a eureka moment. We had the, crap, what have we done wrong moment, where you get the wrong answer. It kind of reminded me of my days in school. But through careful checking, we realized that that's what the universe seemed to be doing, something that has been vindicated over time. So when you measure something unexpected, like that the universe is speeding up, you have to have an explanation for it. The problem we have is we have about 7,000 explanations for why the universe is accelerating right now. And there is no way to distinguish observationally, the stuff I like to do, of which one of those 7,000 theories are right. So guys, do you think any of the 7,000 theories are right?
No. Oh, he does, yeah.
Not those, but the one that preceded them.
Okay. Yeah, so there is a theory. It turns out Einstein had an idea where in 1917 he realized that the universe he thought was steady and he could add energy to space itself, and he could use his new version of gravity with this energy that's part of space that makes gravity push rather than pull, and potentially stop the universe from expanding. That today, that idea of Einstein's, is still our best idea. That is the one that we keep on testing and we keep on getting that it seems to work. So again, those 7,000 new ideas have a problem. Because I cannot use the technology to test those ideas. How do I know if they're real or false if I can't test them? And that's a fundamental part of where we get to in astronomy. Now, astronomers have ways of testing things. We have telescopes of increasing sophistication. They allow us to go through and look at galaxies and map the galaxies out. These galaxies, it turned out, are left over. They're formed where essentially the splashes of material left over from the Big Bang deposited more mass in certain parts of space than others. And so that splashing around after the Big Bang we see in the cosmic microwave background, and we're up here. And so you're really looking back about as close as you can right now to the time of the Big Bang, 380,000 years after the Big Bang. And when we look at that image, it turns out to be smooth to 1 part in more than 100,000. But within that, it turns out there's a couple little funny things. If we look at it very carefully, we see that one half of the sky is a little different than the other half of the sky. And there's this little place where there's a circle there that's a little colder than you would expect. Now, we don't really understand those yet. The question is that information interesting, and information, for example, leaking in from Frank's multiverse? Or is it some little smudgy thing that has nothing to do with anything? We need to have people give us ideas of their theories, and so we can test them as this type of data. And of course, we're getting more and more data. We have the Giant Magellan Telescope that we in Australia are working with Carnegie Institution and University of Arizona and other universities across the United States and Korea to build. We have new generation of radio telescopes that will allow us to look to literally to the edge of the universe that has stars and galaxies and even beyond, to the time before that. This new facility is about 10 years away, but will be of the same scale as the Large Hadron Collider is in CERN. And we have experiments, for example, this one, Euclid, done by the Europeans, dedicated to understanding how the universe is accelerating in great detail. We're not really sure what's going to find, but the knowledge we gain will hopefully help inform the theoretical work that is going on. We also have the ability to look beyond light and radio, the electromagnetic spectrum. There is proposed within Europe, and the US is involved, an experiment known as LISA that looks at gravitational waves. And so, although you can see things like black holes merging, you also have the potential to look back before the cosmic microwave background, literally to the milliseconds, the moments right after the Big Bang, looking through the universe to that signal of the creation of the universe itself that might well tell us things about how the universe was created. So we have lots of data, and that data combined with all these wonderful facilities are the key to trying to understand the universe. But there are some things that may not leak in. It may well be that Frank's multiverse simply does not imprint any information in our universe. No matter how smart you are, there is no signal. But on the other hand, there might be. We don't know unless we look. And that's why observers like myself and Wendy need to work with theorists like Frank and David, and we do our best work when we work together. So the multiverse right now, as shown in this picture called art called the multiverse, is still more art than science because we cannot test it. But my hope is someday we might be able to. Thank you.
Thank you.
I'll take that as
Thank you, Brian.
lower bound.
You remind me of a famous statement by a science fiction writer that reality is that which continues to exist even when you stop believing in it, which should be relevant, but we won't go into that. David Krauss. What can I say about David Krauss?
Don't.
Besides that he's a smart guy who was Frank's supervisor. Many scientists seek out problems they can solve, but the really great scientists, and they come along once a generation, seek the problems that can't be solved. And David, it seems to me, a characteristic of his remarkable career as a scientist is to work on the problems that seemingly couldn't be solved. In the 1960s, the strong interaction between all the new particles being discovered at then accelerators was perplexing, so perplexing that many physicists gave up, threw up their hands, and said the laws of physics as we understand them, special relativity and quantum mechanics, will not allow us to understand all of this mess. And David looked at that and actually tried to prove that fact. But instead, he discovered, along with Frank, that those laws could be combined, in fact, to describe the strong force, one of the four forces in nature. It's for that he and Frank shared the 2004 Nobel Prize in Physics. But that wasn't, again, all. The next, David decided that was a hard enough problem. He wanted a harder one. And the hardest problem nowadays is how to put together quantum mechanics and gravity. And David then proceeded to become one of the leaders in developing what is now called string theory, or often called string theory, as a potential theory to unify quantum mechanics and gravity. It's still a long way from maybe having done that, or maybe having shown that it has anything to do with the real world. But it is been the most ambitious and remarkable theoretical effort that's been undertaken, and David has been a leader in that. And what's really remarkable about that process is that many string theorists have thrown up their hands and said, string theory predicts so many different universes that it can predict anything. And David has said, no, it's going to predict a unique universe, and that universe is ours, and he has been leading the charge to do that with a kind of boldness that very, very few people could possess, and a kind of intelligence that essentially very few people on the planet could possess. So that would be enough, but sorry, David. His most unheralded contribution to science is one that, to me, is the most important contribution he's made to science. When I was a graduate student, I was at a meeting with David in California. He was lecturing, and we were swimming together, and an undertow got me, and David saved my life. That may not be his most important contribution to science, but as far as I'm concerned, it is. David, thank you.
I don't.
You don't need. Okay, that's right.
Whatever. So you'll notice that I'm using my own computer, which proves the fact that Lawrence didn't comment on, namely I'm a control freak. Right. So since I'm the last speaker and everyone has gone over time, I'll try to keep to time. But I won't succeed. This is one of the guys who convinced me to become a theoretical physicist. I'm sure you've all heard of him. When I was a kid and he inspired me, I thought he was God. Later, as I read his papers, I felt that he was a colleague of mine. Unfortunately, he's departed because I would love to hear his view on the multiverse. In fact, one of the reasons that I decided at the age of 13 to become a theoretical physicist, I had no idea what that meant, but I liked Einstein's definition, which was the following. The supreme test of the physicist, and what he really means actually are all the physicists, the theorists and the experimentalists working together, but the goal is to arrive at those elementary laws of nature from which the cosmos can be built up by pure deduction. This was Einstein's religion. It's an incredibly, if you think about it, an incredibly arrogant statement. Einstein was intellectually, if among all the scientists of the 20th century, ambitious or arrogant. But if you think about it, physics has been pretty damn good in achieving this goal over certainly the last 400 years. In fact, for the ordinary phenomena that we observe around us, even the behavior of atoms, the behavior of molecules, which is the basis of chemistry and biology, and so most of ordinary daily physical phenomena are explained, we believe quite strongly, in this arrogant, unrealistic, reductionist sense by a beautiful theory called quantum mechanics, to which we add a very simple law. You all know the law of electricity, magnetism, and with one parameter, essentially, and you got to also assume that nuclei exist, but that's the basis of our reductionist, arrogant explanation of everything we know around us: atomic physics, molecular physics, chemistry, biology. Pretty good. And we've done better in the last century. And we've heard some of the great experiments that have been performed by elementary particle physicists and by astronomers and astrophysicists. We heard from Maria about the great discovery made just recently at the Large Hadron Collider. And we've ended up with what is sometimes called the standard model of elementary particles, a list of basic constituents of matter, and more importantly, a deep understanding of the beautiful laws that generalize Maxwell's theory of electromagnetism to explain in great detail. In fact, Maria couldn't do those experiments where she's looking for one Higgs particle out of more than 1 trillion events which are explained by the theory of the weak and strong nuclear forces that constitute the standard model. What they did recently was add the last nail, or the last confirmation of an important component of this theory, the so-called Higgs, or Brout-Anglaire Higgs mechanism. Now, this is not really a model. I like to call it should be called a theory. So I would call it the standard theory, and it's a theory because you can put its equations on one T-shirt. Not only that, this is just beautiful. Now, I must say, for maybe you don't all appreciate how absolutely beautiful this is. Beauty is in the eye of the, unfortunately, rather well-educated observer. But believe me, if you were to give me more than the so-called 8 minutes, which I think means 12, that Lawrence has allocated, 12 hours I could probably explain to you why it's so gorgeous. And it contains here, everything that, just about every measurement that anybody has ever done on Earth. And that's why these guys are very frustrated, because they try to do measurements that sort of aren't contained here. By the way, of course, I have to add this Einsteinian term here that explains gravity, and this cosmological constant, or vacuum energy density, that Brian and friends discovered. This is it. It's all on one T-shirt. It is unbelievably successful. It, in some sense, in this very arrogant reductionist sense that we never follow in practice, but we believe we could, works from the edge of the universe. It explains stars and galaxies far away, and indeed the expansion, if you add this cosmological constant term, to what perhaps are the smallest possible distances imaginable, which are extraordinarily small, 60 orders of magnitude. When I grew up as a graduate student, experimentalists wouldn't trust a theorist to extrapolate by a factor of 2, much less 10 to the 60. Nowadays, they have slightly more respect, right? But when you look, those of us who really look at this carefully don't like it, can begin to see its flaws. Just like if you look at anything really beautiful carefully with a microscope, you see the pimples. So, for example, here we have these terms here, which explain the quark and lepton and neutrino masses, which our friends have measured, so we know what parameters to put in here, but we'd like to understand the patterns and the numbers. Einstein told us that everything has to be calculable. In fact, he once said that if you have a theory with a parameter that appears in it, and you measure it to be 2.56, it had to be 2.56. The theory should be so strong that if that number was 2.55, the whole theory would collapse. That's how arrogant he was. Well, these numbers are arbitrary, and we're always surprised by the measurements that they come up with. It's not just that. We have other features here, one that Frank referred to, this parameter theta, which has many mysteries associated with it. And then we have quantum gravity, the quantization of Einstein's term, explanation of gravity, which we don't yet understand in many ways, many problems, conceptual and otherwise. And then we have this term that Brian discovered, so-called dark energy, or the cosmological constant, which is extraordinarily small, it would appear. So there clearly are pimples and faults in this gorgeous realization of reductionism. What should we do? Well, we certainly must take advantage of the experimental observational possibilities that lie just before us, both in the realm of the universe, with new telescopes and new methods of observing the history of the universe, like gravitational waves. And in my area of elementary particle physics, it is incumbent on the human race, I believe, to fully explore the range which the LHC is just opening. Now, luckily, there are a lot of people who are thinking of new machines, not just in the sky, as Brian discussed, but on ground, something called the Linear Collider, a bigger version of the LHC, either at CERN, conceivably even in the United States, although one wonders whether this country has lost the ability to dream big dreams. And perhaps in China. And we need that desperately. We need those experimental clues. Experiment does more than what Bryant said. Bryant said that science is an empirical effort. We only test our ideas and we only believe them. We continually must test them. That the only way we gain belief is by testing them and not falsifying them. However, experiment plays another role of suggesting whole new areas, new questions. And when, after constructing the standard theory, Frank explained that the forces, when extrapolated theoretically, seem to come together and unify at this incredibly short distance scale, the so-called Planck scale, where gravity also becomes an important and quantum phenomena. So for the last 35 years or so, we've been focused on this idea that this is where the interesting physics is going to happen, and yet we only observe at much, much larger distances. We're not going to get here soon, but we need clues as to what goes on there. What is that sacred scale, the Planck scale, where the forces unify? It's called the Planck scale because when Max Planck discovered his quantum constant that denotes the boundary between classical and quantum physics, he understood that he had finally enough fundamental constants of nature to define the fundamental scales of physics. And the weird thing is that they came out to be so incredibly small or fast or heavy in natural, not only natural units, but atomic units, nuclear units, so far removed from where we can explore. It's what I call the curse of logarithms. It's a fact of nature which Planck already understood and all physicists afterwards. You see, when we draw a scale of different kinds of physics, different kinds of machines, and something is cutting this off, we use often a logarithmic scale of energy. On that scale, atomic physics was first understood by Rutherford by using 10 to the minus 3 GeV alpha particles. The strong interactions, which we worked on, was discovered by using 100 GeV accelerators and beams. Factor of about 1,000 more. And the weak interactions are now, the scale of the weak nuclear force is now being explored. Higgs particle discovered at the LHC at about 10 to the 4 GeV. It's very important that we go on, at least, I think, the 10 to the 5 GeV to cover this third force. But the fourth force, which defines the true scale of unification of the forces, we know is up here at 10 to the 19 GeV. But if you look at this logarithmic scale, well, it's not so far. You go from atomic physics, to strong interactions, to weak interactions, to gravity. Maybe it's a little bit more, but we've done it 3 times. Once more is a cinch. The trouble is that dollars is measured on a different scale. Effort, dollars, doing such experiments goes more like energy squared. And on that scale, Fermilab is cut off here, right? But it's around here. The LHC is an enormous step. The next step is, okay, not so big, so we can easily do it if we had the will. Rutherford is about 10 miles down that way, and the Planck accelerator on this slide is about 40 miles that way. But that's a fact of nature. We can't do anything about this disparity of the way physics varies. The essence of physics varies logarithmically with scale, and the effort it takes varies linearly or quadratically. And we have so many questions that require clues or measurements to both suggest new things or test new ideas, like string theory, the structure of space-time, which many of us working in this field believe is likely to be an emergent concept, gravity as well. And then, of course, the questions that Brian addressed, having to do with what goes on at the beginning, the Big Bang starts this inflation, and what happens at the end with this cosmic acceleration. Well, I'm an optimist, and I believe that most scientists, in fact, all good scientists are optimists. Why? The bad ones leave the field. I mean, the pessimists leave the field. You have to be optimistic to work on hard problems. But I really believe that once a fundamental question becomes well formulated scientifically, by which I mean that it's approachable by experiment, by observation, and by mathematical modeling, theory, it will be answered in your lifetime. Not necessarily in my lifetime, but that is really good news, if I'm right, because we've been discussing a lot of wonderful questions. And for those of you who are young, they most likely will be answered. That's the story of the history of science in all fields for the last few hundred years. Conversely, once an important scientific instrument is technically feasible and addresses fundamental scientific questions, it will be constructed in your lifetime. That's also proven true. So those are really reasons to be optimistic. New discoveries, which will be made, I believe, in my lifetime, dark matter, supersymmetry. New tools, even in the case of particle physics, which change the way we build these expensive big accelerators, like plasma wake field acceleration, which might allow you to build an LHC in your backyard. And new ideas. Theory can do that. Copernicus did that, Einstein did that, Higgs did that, et cetera, et cetera. It actually becomes easier the more we know and the more constrained our theoretical extrapolations become. So, as everyone has intimated here, and I strongly believe, the best is yet to come. Thank you.
Thank you, David. Okay, thanks, David. You can, but thank you very much for the 8-minute talk in a logarithmic sense.
Well, I was just following your and others' example.
No, there's a lot to talk about. As you indicated, we're stuck with the universe in which we live, with the Planck scale where it is, and most of us are stuck living in the universe in which we live. Most of us. I was going to say one political party isn't, but I'm not going to get there. But that's an interesting question, because that is not just the fact of life, but it's a fact we have to live with every day. And the question is, if you were a doctor and you had access to one patient in your life, and that patient came into your office and they were 7'5" and 450 pounds, what would you say about humans if you had access to one patient? We have access to one universe, and we see that little spot, that cold spot that Brian pointed out.
Yes.
Is it significant, or we just have bad luck? Those are the kind of questions we're going to try and discuss by answering your questions after the intermission. Thank you very much.